In this video, we will be looking at the time value of money. This isn't really the normal type of videos you see in specific topics. I thought it's important to go over this because it's going to help you a lot in the future, like in your life. And I wasn't sure where else to put it within like the categories we have. So I think putting it here would be probably the best option. It's not really what it's not a very complicated lesson. It's just a good thing to understand. And yeah. So we're gonna go over four concepts. One is very quickly is I'm gonna explain what is time value of money. Then we're gonna look at compound interests. I'm gonna introduce future value and present value. And then we're gonna look at annuities. We're gonna talk about annuities, what they are, two types. We're going to look at the future value and present value formulas. And then we're also going to look at perpetuities. We're going to explain future value and present value. And then within those, we're going to talk about cash flows. But yeah, it's very, very simple. It shouldn't be a long lesson. And let's talk about time value of money. So what is time value of money? So the time value of money means $1 today is worth more than $1 tomorrow. And you could think of it in a way of, if I offered you $1,000 now or $1,000 in 1 year from now, which one would you take? Well, you could take $1,000 now and invest it. And let's say, a bank's offering you 5% interest monthly. So if you take that $1,000, and I'm just quickly do the calculation monthly. So for 12 months, that $1,000 is going to be $1,795. Now, obviously, that's a big amount. Usually, when a bank offers 5%, it's 5% yearly, and then that 5% is broken down into 12s. There are three big reasons for this. So there are definitions that relate to time value of money. First is opportunity cost. So in this case, by not taking the money now, you miss out on the investment gains. That is your opportunity cost. There's inflation, so money loses purchasing power over time. As inflation increases, the value of money goes down. Not like actually goes down, but I'm in the sense of like $100 now and $100 in 5 years. That $100 now will buy you more than it would buy you in 5 years if inflation is consistently increasing. And then risk, obviously, you're not guaranteed to get the money later. So now we're going to look at interest. We're mainly going to talk about compound interest, but I'm also going to mention what simple interest is. So simple interest means you earn interest only on the original amount. I'm going to show you an example. So let's say you have $100 and you get 10% interest. So you're going to receive $10 each time. So it'll be 10, 10, 10, 10, 10, 10, 10, 10. So your account will increase by 10 each month. So your account will be 100. Then at the end of the month, it'll be 110. And then that 110, you're not going to take interest from that. You're going to take from the original amount you deposited. So you're going to have 100 again. So it'll be another 10. So basically it'll be 100, then 10, 10, 10. So the interest is only calculated once at the beginning of what the account balance is. And then you get that fixed interest each time. So it'd be the same amount. On the other hand, I don't really know any bank that uses simple interest. Nobody likes simple interest. You don't really make money from that. Unless you have like a lot of money, if you have like $10 million and the bank is offering you 2% interest. So then sure, but I don't know. Now the one that everybody knows and talks about is compound interest, and it's in the name, it compounds. So it means you earn interest on your money and on the interest that money has already earned. So if you have like $100 you put into account and you have 5% interest, your first month 5% of 100 is $5. So that 100 will become 5. But then the next month, you're going to take 5% of what's in the account. So now you're taking 5% of 105. So you're going to receive a little more than $5. And then it keeps going on and on and on. So we could show those two examples. So if simple interest, start with $1,000 and 10% interest rate. Year 1, 2, 3, it's just continuously going to be $100 because we're taking 10% of this amount only. So then the value of year 10, you're going to have 2,000. Now, on the other hand, we could do compound interest. So start with $1,000 and then we're going to receive 10% interest on that each time. So 1,000, we take 10% interest on that. We make 100 year 1. then in year 2, we're taking 10% of $1,100, which would be 110 and 121 and so on and so on. And on year 10, your interest is actually 236. And so if we look, we can see that at year 10, from interest alone, you're making $236 compared to your 100 in year 10 on simple interest. So it's very, very simple. Now you may wonder how we calculate this. Well, we have formulas. In this case, we're looking at the future value. We're looking at what the value is in the future. So we have this formula here. Future value is equal to your present value, how much you have now, multiplied by the interest rate, 1 plus the interest rate to the power of how long. Future value, R is your annual interest rate. So in this example, actually, we have 10%, and then T is just the number of years. It's also important to understand that your interest rate is written as a decimal. So 1, when R is equal to 1, that is 100%. And in this case, we have 10%. So R is going to equal to 0.1. You could just do this by taking whatever your percentage is and dividing it by 100. So if 10% divided by 100, 0.1. So R is written as a decimal. So we're going to prove this example. So we know that year 10, we're saying that the future value at year 10 is 2,594. And if we put it into the equation, we have future value is equal to our present value, which is 1,000, multiplied by 1 plus your interest rate of 10%, so 0.1. This was to the power of 1. This is for first year. The 1, it gives you that. Now for the second year, for year 10, you do 1,000 times 1.1, if you add these, to the power of 10. If you put that into calculator, we have 1.1 to the power of 1.1 to the power of 10, which is 2.5937 decimal. Then when you multiply that by 1,000, you roughly get 2,593.74246, which just rounds up to 2594. Now that is your future value. We could also do the opposite. What if we're given this future value and we want to find the present value? So this is compound interest present value formula. And the only thing that we do here is if you were to write these out like this, we have future value is equal to PV times whatever, all this, the power of T. To find the present value, all you have to do is isolate. So this goes here and, 1 second, I'm blanking. Okay. You crisscross these, your present value goes here, and then your future value goes here, and then this goes to the bottom. It's simple math. I know it looks really bad the way I'm drawing it, but it's simple algebra. So we could see we have present values now. All the present values equal to this, and then all these variables are the same. And we're going to prove last example. So we know that in 10 years, our $1,000 with 10% interest would be $25.94. But what if we don't know we started with 1,000? So we're going to see what value we started off 10 years ago. So we find our present value right now. We put in our future value. So in 10 years, we have $2,594 divided by 1.1 to the 10 because it's been 10 years, which gives us 1,000. But let's say this is the value at year 5. So we know that we have a value right now. And then in 5 years, we have $25.94. So $25.94 over 1.1 to the 5. That means right now we need to deposit $1,610.67 to have $25.94 in 5 years. Very simple. So that was pretty much the easy stuff when it comes to time value money. You don't really need to know this, but this is also really good to know. There are 2 more things. Like I mentioned, there's annuities and perpetuities. These are kind of like interests, but they accumulate in a different way. So in finance, an annuity is a series of equal payments made at irregular intervals, and they're like a monthly pension, a car loan, rent. There are 2 main types. There is an ordinary annuity, which is the one we're going to talk about. These are payments made at the end of each period, and annuity due is payments made at the beginning of each period. So like I said, monthly rent, car payments. Just here's some examples. So future value of annuity. Annuities both have future value and present value. So for future value, an ordinary annuity, we have future value is equal to your payment per period, which is kind of like not really a present value, but it's your payment. So, instance, if you have to pay something $200 a month, then this would be your payment value, and it is equal to 1 plus r to the t minus 1 over r, where r is your interest rate per period, and t is a total number of periods. So if you're looking at 10 years, so in this case we have 10 years, but we're doing it monthly, so we have 10 years times 12 months, which is 120. So your period would be 120. So you could kind of look at this at, like, you could imagine it as equal deposits every month into an investment account. There are a few key ideas. So each payment grows for a different amount of time. The first payment compounds for the entire duration. The second payment compounds for one less period than the first one. And then the last payment doesn't compound at all. It's made right at the end, right? Because it's at the end of the ordinary annuities at the end of the period. So you're really adding a bunch of compound interest formulas, one for each payment. And then instead of calculating each one individually, we use a geometric series. So this would be the geometric series to calculate this. So we're going to break down this formula just a little bit. So right here, the hardest part is this inside the bracket, 1 plus r to the t minus 1. This captures how much each payment grows over time, and we're summing it up all those compounding effects in this equation. And then the reason we divide by r is because it's a geometric series, and this part adjusts for the interest rate across all periods. So we have to adjust it to the interest rates we have. And then obviously the reason we multiply by p is since each payment behaves the same way, we just scale the result. So we scale it by the monthly payment or the yearly payment or whatever it is, usually monthly for annuities. So here we go. In this example, you invest $200 every month into a portfolio earning 6% annually for 10 years. Now, the catch is 6% is annually. So first we're going to convert the 6% into a decimal form, which is 0.06. And then since we're compounding monthly, we need to convert this annual payment into monthly percentages. So we take 0.06 divided by 12, and our monthly percent is 0.05. So it's going to be 0.5%. And since it's 10 years and we're talking monthly here, we're going to take the 10 years multiplied by 12 months to get 120. Now all I have to do is plug it into the formula. We have 200 is equal to 0.01 plus 0.05 to the 120 minus 1, and then that is divided by 0.05. I do want to mention that this, I don't really have the tool. Do I have the tool? But this, imagine there's a bracket here. This gets calculated first, and then whatever this is, it gets multiplied by 200. This would be a big bracket here. Yeah, and then once again, reminder, R is written as a decimal, and then future value in this case is $32,775.87. That'd be the future value of your investment. So you're gonna earn $200 every month for 10 years, so 120. So you could do 120 times 200. This is your base, 24,000. But with all the interest you're making money, if you subtract 24,000 minus 32,775.87 and take the absolute value, you make $8,775.87 just from interest. So that's basically what it's saying. Same thing, but the reverse, you have your present value. So the present value, we kind of just swap out the formulas. So present value is equal to your payment per period multiplied by 1 minus 1 plus r. Now the big difference between this one is we take the negative total number of periods, and this is what brings us back to our original number. And you may wonder why this formula works. So each future payment is worth less today because the time value of money. So instead of compounding them forward, we're discounting each payment back to the present. And then, like, again, instead of discounting every single payment one at a time and adding them, we use a shortcut for the sum of discounting cash flows. So right here, we're going to explain this real quickly. This brings back the value of all future payments paid today. The 1 minus that right here, because we want the value of payments combined, dividing by r, again, adjust the sum for interest rates, and multiply by p applies the result to the recruiting payment amount. So this would be the scale multiplier. For this example, we're going to take a loan with $300 monthly payments for 5 years at a 5% annual interest. 5 years multiplied by 12 months to get it monthly, and then we have 5% annual interest. Break that down, divided by 12 to get the monthly interest. plug it into the formula, and we get 15,897.24. And that's the current value of those future payments. And so that's how loan companies determine what to lend you today to see how much it's worth in the future. And yeah, so last thing we look at is a perpetuity. So a perpetuity is a stream of equal cash flows that go on forever. Some examples are preferred stock dividends, perpetual bonds, and endowments that pay out forever. So the present value of perpetuity is very, very simple. You take your present value and you do your payment per period simply divided by interest rate per period. And since the payments go on forever, you can't use a geometric series like an annuity. It would never end. And so what we have is math has a trick for that. And when a series goes on forever and each payment is the same, the total value converges to a simple ratio. It's a very, very long one when you go to infinity. And you could think of it like this. So if you're earning $100 every year forever and your required return is 5%, you'd be billing $2,000 now, because 2,000 multiplied by 0.05 is 100, and that makes it fair. So we're going to show you this quick example. You're promised $250 every year forever, and the interest rate is 4%. So you will receive $250 every year forever. And obviously the normal person doesn't live forever, but if they were to live forever, $250 discounted to this year's interest rate is $62.50. And I'm going to show it to you right now. If you take 250 and do divided by 1.04 to the 1, you get a small number. And as you keep adding up those values, so as you keep finding the present value, what happens is the decimal gets, the interest rate gets square rooted to such a high number to the point where as time goes by, you're adding on very, very, very little. And the addition adds so small that it kind of becomes like a limit function in a way. So if I were to draw this out, like, wait a second. So if I were to draw it out, what happens is you start increasing money, but it starts slowing down to the point where it kind of just flattens out to a point and where it reaches a max. It's like a limit function. So in this case, 250 divided by 0.04, it gives you 625. So that top limit would be 6,250, and it will never go higher than it because it will add such small decimals. Now, future value of a perpetuity. Well, there is no formula for the future value of a perpetuity. Well, you may wonder why. Well, because the reason there is no future value is because the payments never stop. It's infinite. So there's no final point in time to evaluate the total value. The future value would be infinite, so it's meaningless in its financial modeling. So a few takeaways just for this. So present value is the value of infinite payments today, and the future value doesn't exist since cash flows never stop. And then, actually, no, back looking. And then a quick summary for perpetuities. So a perpetuity is a stream of identical payments that last forever. Since there's no end, you can't calculate a future value, but we can calculate what it's worth today. And then your present value is simply your payments divided by interest rate per period. And yeah, so quick recap, $1 today is worth more than $1 tomorrow because you can invest it. Compound interest grows your money faster than simple interest because simple interest rate is a fixed payment, while your compound interest payment grows because there's more value. There's more money in the account to be compounded with interest. Present value tells you what future money is worth now, and annuities and perpetuities help us value repeating cash flows. That's it for today. This was a very, very quick lesson. I just want you to understand the basics of compounding interest. This is very good for when you're doing long-term investing. You want to understand these basic formulas. And yeah, I hope you enjoyed this video, and I'll see you guys in the next one. Thank you.